Hello, my name is Thomas Veelen from Swansea University, and I also work at the consultancy Möller and Schuurmans. And today I would like to share my research about nature-based coastal protection by salt marshes, and in particular those with flexible vegetation. So salt marshes, they're vegetated intertidal wetlands with very diverse vegetation, ranging from very rigid shrubs to very flexible grasses. And they're of course most appreciated within the coastal engineering community for their function as a nature-based flood defense. They attenuate currents, they stabilize shorelines with their roots, and perhaps most importantly, they also damp incoming waves. And for the latter part, we of course try to quantify how much the waves are being damped by the salt marsh vegetation, and for this we distinguish between rigid vegetation that doesn't move and flexible vegetation that does move. Rigid vegetation is the simplest case which just affects the wave forcing, provides drags to the waves, which leads to a reduction of wave energy and then to lower waves. This has been solved first for regular waves by Dalrymple et al. In 1984, and later this framework has been expanded to random waves by Mendes and Lozada in 2004. On the other hand, the case for flexible vegetation is much more complicated, as under the wave forcing the plants will move, which then again affects the wave forces. So to solve this system, 4 methods have been trialed. First of all, beam theory, but is only applicable to salt marsh species with limited excursion. Second of all, the scaling analysis, which simplifies the force balance, but leads to a set of equations that currently still relies on a form of calibration. Thirdly, there's plant scale computational modeling, which is very accurate, but also very computationally heavy, which makes it unsuitable for large coastal areas. So the method that's actually used most commonly in practice is the calibration of a drag coefficient. Same assumption of rigid vegetation are being made, but the drag coefficient is then calibrated to correct for the assumption of rigid vegetation. But it has been shown that this drag coefficient can differ by 2 orders of magnitude, so it's very sensitive. And there is then no method currently that's applicable for all plant species that's computationally efficient for large-scale application and doesn't rely on calibration. And the objective of this research is to provide such a modeling framework that is both fast, can be applied for all flexible vegetation species, and does not rely on calibration. To do so, we look at 2 parts. First of all, we identify the key processes in the wave-vegetation interaction, and secondly, we build a matching modeling framework. We will also have an outlook into future applications, and we will draw some conclusions. Part 1, the wave-vegetation interaction. To understand the wave-vegetation interaction, we conducted experiments in the Swansea University wave flume with artificial rigid and artificial flexible vegetation, and we measured the wave heights, we measured the water particle velocities using PIV, and we also measured the vegetation motion of flexible vegetation. So how did experiments look like? There's 2 videos of both the rigid vegetation and the flexible vegetation, and you see the particles which show the water particle motion. And what we find is that both the rigid and flexible vegetation damp waves, but there's significant difference. The rigid vegetation damps waves up to 3 times more as the flexible vegetation. So we try to understand what is really important in solving this interaction between plant motion and wave forcing. To do so, we first look at the most important forces based on our measured water particle velocities and the vegetation motion. And we find that the drag force is dominant, especially in the bottom and middle section. In the top section, the added mass force and fruit force are of similar magnitude, but are of much smaller magnitude than the drag force in the lower sections. Second of all, we compare the stem reconfiguration effects against the stem velocity effect. The stem reconfiguration effect here is the fact that the plant bends under the wave forcing, due to which the horizontal component of the wave forces, which is typically dominant, becomes less important, and because the horizontal component is usually the largest component of the wave force, the total wave force that total wave force that is being dissipated reduces, which leads to less wave damping. And secondly, we have the stem velocity effect, which considers that because the stem moves, the velocity difference between the water and vegetation reduces, and due to that the wave forces reduces, and also the wave dissipation reduces. And we find that the second effect can explain 92% of the reduction of wave damping over flexible vegetation. Thirdly, we find that energy is dissipated where the stem is upright. For rigid vegetation, energy dissipation is distributed uniformly over the whole stem, whereas for flexible vegetation, it's really concentrated in the bottom section of the stem, which is upright and also relatively immobile. So these are the three key physics. Based on that, we built a modeling framework. So the three key physics are turned into modeling assumptions. The first modeling assumption is that all energy dissipation is due to the horizontal component of the drag force. The second assumption is that the stem is near vertical with horizontal motion, even when vegetation is very flexible, and that's justified because we find that the bending effect is much less important than this velocity effect that we really capture with our modeling assumptions, and also that the energy is dissipated where the stem is upright. And finally, while not directly derived from our key physics, is that we use a pre-selected drag coefficient based on Hu et al. 2014, so it doesn't rely on calibration. Under these modeling assumptions, the plant motion is now governed by a force balance between a bending term and the drag force, and this equation can be solved by an expansion into spatial temporal modes following Mullarney and Henderson 2010. So what happens is that we can project the water particle motion on the spatial temporal modes, and based on that we can solve the system of equation and find the vegetation motion, which we can then use to find the wave forces. And what we're really interested in is the wave dissipation, and into this component we introduced a new flexibility factor. So we found that the wave damping formulation by Mendes and Lozada could be maintained, and only this flexibility factor could be introduced to correct for the fact that flexible vegetation generates less wave damping. And this flexibility factor G is a simple function of the differences in phase and velocity magnitude between water and vegetation motion. And this leads to a wave damping factor beta, of which is important that a higher beta means a higher wave damping. And this beta is also what we validated, of course against our own experiments, but to really challenge ourselves we also validate our model against large-scale experiments of 3 real vegetation species, Spartina anglica, Puccinella maritima, and Elymus ethericus, all semi-flexible to very flexible species, with the wave damping over the species differing up to 2 orders of magnitude, which is successfully reproduced by our model. This is for regular waves, but the same goes for random waves bar 2 outliers that you see. But for the rest, again, the magnitude of wave damping is very successfully reproduced. And a quick outlook to the application. As said, our model has been designed to be also really fast and easily applicable for coastal areas. We're looking to apply this in estuaries with very diverse salt marsh vegetation, where calibration would usually take a lot of time, but now we can see that depending on the vegetation characteristics, we can see that the wave field already differs, and we're looking to explore this much further in a later stage. Finally, we arrive at some conclusions. First conclusion is that salt marsh vegetation dampens incoming waves depending on the vegetation flexibility. Secondly, we find that the wave vegetation is controlled by 3 key processes. First, that the drag force is dominant. Secondly, that the stem velocity dominates stem reconfiguration. And thirdly, that the energy is dissipated where the stem is upright. The wave damping can then be effectively modeled using a flexibility factor that we introduced, and using this model we can again show that wave damping over salt marsh species can differ by multiple orders of magnitude, and that it is successfully reproduced by our model. And in the future work we will be looking to apply this more also to real salt marshes. So thank you for watching, and if you have any questions, feel free to get in touch, and goodbye.